Hi, Shadab.
Hi.
Hi.
Okay, everybody, welcome to today's Majorana-Raychaudhuri seminar series. Today we have three speakers, and the theme of today's topic is the recent DESI measurements and the theory interpretations and experimental results. And we'll have three talks. First by Shadab Alam from TIFR India. So maybe let's begin.
Thanks, Anish. Should I share my screen? Is that all
Yes.
right?
Yes.
I hope you can see my screen in full screen mode, in presentation mode.
Yes. So Shadab will be talking about hints of evolving dark energy, and we will have 30 minutes for your talk. Shiladitya will send you a reminder when 5 minutes are left.
Great. Thank you. Thanks a lot, Anish and Shiladitya, for inviting me to this interesting seminar series. I'm really happy to talk about this recent result, which is a hint, as my title says, hints of evolving dark energy. Please feel free to interrupt me if you have any question. I'll try to give a flavor of it as well as some a bit more insight in terms of how these kind of measurements happen. Okay, so let me start by very basic so that all of us are thinking about quantities in similar fashion. The one of the really important thing in cosmology is to be able to measure distance. And as we all know, if you want to, well, if you are living in a Euclidean two-dimensional space, you can measure distance in using Pythagoras theorem, which is given by ds square, the distance element as square sum of the two axes. Now, if you're living on a surface of a sphere rather than this two-dimensional flat geometry, then the distance metric is going to look different. And so you'll have to define what is the distance metric on the surface of a sphere, which is given by the spherical polar coordinate transformation. And the distance metric will have a term which is no things are no more independent, as simple as in Pythagoras theorem. And so this idea of being able to define distance on a particular geometry is what we call metric. And that's one of the key things when we think about dark energy is something you have to understand and appreciate. So in the context of cosmology, if you think about that, we are living in homogeneous and isotropic universe, and that itself has two question marks, which we continue to evaluate and understand. But if you think that our universe is a maximally isotropic and symmetric system, then you can think about space-time geometry is something which is expanding with this with a quantity what we call scale factor a of t, and you can write the metric in FLRW metric space, where you can separate the time component with the spatial part, and the spatial part, the expansion can be essentially taken out because of the homogeneity and isotropy, and can be all encapsulated in a square, so scale factor as a function of time. So much of the background cosmology, or when we talk about dark energy, is really trying to understand this function a of t. What are the quantities which govern this function from theoretical point of view? How can we have a handle on this function? What is the evolution of this function as a function of time? And so to probe that a little bit deeper, you might want to think about this function as a different component. And so often we think about the first derivative of quantities if you want to look at. And so we can define the first derivative of scale factor and scale it by the scale factor itself. And this is exactly what we call Hubble rate. So you'll encounter Hubble rate at several places in my talk. And then if you want to look at in GR framework, and then look at what are the equations which can help you derive what the scale factor look like. That's basically the Friedman equation, which essentially connects how this first derivative of the scale factor connect to the content of the universe, matter density, as well as if there is a cosmological constant. And then the second Friedman equation connects to the scale factor, double derivative of scale factor, which essentially talk about whether the universe is accelerating or decelerating and how fast the acceleration looks like. And then that connects again to the content of the universe in this fashion. And so if you know content of the universe, and if you know the how they evolve, you can in fact work out how the A of t looks like, or including its first and second derivative. Now, in an expanding universe, you might want to think about how the content of the universe itself evolved. So if you imagine a system of, let's say, box L, and you scale it by scale factor AL, so in this diagram, A is certainly bigger than 1, just for the illustration purpose. So the cube is bigger on the right-hand side. And if you think about different quantity, for example, matter, which density can be defined as mass content in this box divided by L cube, then as you expand it with A, it's going to reduce by A to the minus 3 because the volume is increased by A cube. If you think about radiation, then apart from the number density dilution, as we have seen as A to the minus 3, the energy of photon is also going to get dilated because the wavelength of the photons are going to get stretched. So SC over lambda is going to be SC over A lambda. And so that will give an additional factor of A, and so it will look like A to the minus 4. So radiation will go to A to the minus 4. And if you think about there's a cosmological constant vacuum energy, this is something we don't know. If you propose that this is a quantity whose energy density doesn't change as the universe evolves, then lambda will stay lambda. That's by definition, and so it will go as A to the 0. And so when people think about cosmological constant or dark energy, this component which is causing acceleration, one of the key thing is that whether this energy density, does this stay constant or it's evolving as a function of time? And if it does evolve, then what is the factor of A? If we can write down in similar fashion, then what will be the factor of A is relevant. And so you can write in general all of these things in the form of equation of state. And so energy density of anything is going to go as A to the power minus 3W plus 1, where the W is the equation of state. And if you put W equals to 0, that will give you matter. If you put W equals to 1/3, that will give you radiation. And if you put W equals to minus 1, that will give you cosmological constant. So I hope it's very clear conceptually, physically, what we mean by equation of state when we think about these kind of quantity. And so that's the rest of the talk is going to talk about what the equation of state mean and how can we measure that. So to build a little bit more intuitive picture, if you have, let's say, measurement of early universe, for example, CMB, you can estimate what are the initial densities of matter and radiation in the universe. And since we know how these things scale as the universe evolves, A to the minus 3 for matter and A to the minus 4 as radiation, and our initial condition measurement says that radiation was much more abundant than matter in the beginning, this will predict a very important era in the universe, which is radiation matter equality. A lot of interesting thing happens, and we are still trying to probe this carefully from large-scale structure survey. And then if you look at local universe, so at small redshift or scale factor close to 1, then at some point matter density will be even subdominant to a cosmological constant, if you know what is the amplitude of that is. And so this is what we call dark energy dominated era of the universe, which is the current, and that's really the recent past, and so not for that long, for W equals to minus 1. And so by looking at different observable, you can probe different part of the universe, either the radiation matter equality or early universe, if you look at the CMB. And if you look at galaxy surveys in the in the recent past, then you're mostly looking at this era. And if you look at below redshift 0.7 or 8, then you're looking at this era where dark energy is dominating. And so you should be able to see the dynamics, if any, of dark energy. So dark energy is something really interesting and remarkable right now, one of the biggest puzzle. And based on the current estimate, if it's within the lambda CDM framework, if you look at the current measurements, this is about 70%. The exact amount will depend on what kind of models you're considering and things like that. But it's about 20% in the current universe. It's not going to change by much. And so one of the main question we are trying to ask right now in the dark energy space is what is the equation of state of dark energy, and whether the equation of state of dark energy evolves as a function of time. So is there a time evolution of equation of state? So this is essentially the ratio of pressure by dark energy divided by the density of dark energy as a function of time. And so if you can understand whether this evolves or not, you can go back to all the pictures I've drawn before and then think about how different era of the universe is going to operate and what will the dynamic look like in terms of the expansion of the universe itself. So different models, whether you proposed the acceleration of the universe is because of the cosmological constant, or there are models which propose this is modified gravity, there is a modification in general relativity itself. There are models with extra dimension in string theory, as well as single and multiple scalar field. All of these things, if you write down the specific Lagrangian of one of these models, it will predict a specific dark energy state evolution. And so by measuring this evolution, you can also have handle on some of these fundamental physics if it matches with one of the prediction from one of these scenarios. So one thing, although you should keep in mind that this has even beyond just dark energy implications, by understanding the nature of equation of state, you might be able to say something about fundamental nature of gravity, in the sense that what is really the source of gravity beyond the fact that Einstein field equation operates, and so what is the origin of that field equation itself. And so Paddy famously quoted this in one of his paper, that even if you can get away with lambda, the fundamental nature of how gravity originate is something you still need to explain, and why lambda vanishes, whether it's small or it's exactly zero. Either case, you'll have to think about that, and that will continue to be one of the important problems. So now if you think about acceleration of the universe itself in the expanding space, you can think about past, today, and future. And so I can draw this diagram, which on the top panel, it shows the scale factor as a function of time. So this is what is defining how the universe is expanding. And then you can talk about the second derivative of this scale factor, a double dot, which is connected to the second Friedman equation. And so if you think about the matter to be universe to be matter only universe, then you'll expect a scale factor evolution of this form as shown in this line. And what you'd expect is that if you remember the equations I showed you, the first part of the matter was negative, and so universe is decelerating, and this deceleration start to fades away because the scales of the universe is increasing, and so the effect of matter is almost disappearing, and finally it will go approach zero. It will never go to acceleration phase if it's matter only. But since we have observed acceleration from supernova starting from about 2000, and there's even a Nobel Prize given to that, there's no denial that universe is accelerating. It's a very strong evidence. And so if you put in a model saying that acceleration is because of a cosmological constant lambda, which scales with a to the 0, then you'll find the best fit model would look something like this white line, where the universe is decelerating in the past, and at some point it is start to accelerate, and then it goes faster and faster. Now, this is when equation of state is equals to -1 cosmological constant, but you can also think about cases where equation of state is bigger than -1, so this is quintessence or additional scalar field. For example, if equation of state is -0.5, you'll get the green line, where the deceleration phase is basically same as the white line, but at some point it goes to acceleration, but it's a very small amount, and it will saturate to again deceleration phase. The detail will depend on what the value of equation of state itself is, but it's constant and greater than -1 in this scenario. You could also think about phantom case where equation of state is less than -1, and the reason this is phantom is because this will have lots of issues in terms of the overall behavior of the theory. And what you'll see is that in this case, the acceleration gets even much faster and faster compared to lambda CDM, as shown by SAN line, if W is less than -1. And if you look at the best fit W values obtained through a DESI experiment, both DR1 and DR2, then you'll find that in this kind of diagram, you'll find the red line where you're decelerating, but then universe goes to the acceleration phase, and then the acceleration drops back. So there's a maximal acceleration which universe would have had obtained at some point in the past. and then it's dropped down, and then it will go to deceleration phase again, which will again dilutes and then go there. So this is one particular parameterization where the main feature you want to look at is that the acceleration itself has a different nature compared to lambda CDM. And so this particular model, if you parameterize it in CPL parameterization, which I'll talk about again in detail. So there are caveats to this plot, but in that space, then what you'll find is the allocation of state crosses -1. So it was below -1 at some point, and then goes to above -1. And this is very strange in sort of minimal theories. So there is a no-go theorem which says that this is very hard to do in simple theory where there's no dark energy, dark matter interaction and a simple models any kind of single scalar field theory. So you need to think about dark energy being represented by more than one fluid. So that's the most recent result from DESI, and then we can talk about what the implication is and what the statistical significance is. But one of the thing it's important to point out that in this diagram, I was showing both past and future, and so you're able to see the differences very clearly in all of these parameter evolution or the evolution of scale factor. But remember, we never have access to the future, especially maybe in some scenario you might have access to future if you can exploit the quantum mechanical nature of these things. But otherwise, you never have access to the future, and so you can only observe things today and in the past. And if you look at just today and the past, these models look much closer to each other than what it would look in the future. And so this is why one of differentiating between these lines now just by looking in the past is a much bigger challenge, and why this has been at the forefront of dark energy research at the moment. So just showing that in terms of equation of state, what I already showed you in the form of red line, if we can plot W of Z, where Z is redshift, I will describe redshift in a bit more detail in next few slides. But Z is analogous to a scale factor. You can interchange them. It's A is 1 over 1 plus Z. Then if you can parameterize the equation of state as a function of Z, which is the parameterization is CPL, which essentially has a W naught and WA, two parameter model, then you'll obtain a constraint like this, where the cosmological constant is shown by this black dashed line. And so this is a 2.6 sigma measurement between DESI BU and CMB from DESI year 1 analysis. So that's about 6 million galaxies. And if you combine with different kind of supernova, then the statistical significance changes from 2.6 to 3.5 or 3.9 if you were to use DS year 1 supernova. So this was at the end of year 1 analysis from DESI. And if you fast forward it to this March, this is year 3 result with about 14 million extragalactic objects measured through spectroscopy. And so now our results are much more refined compared to previous one. And so DESI plus CMB plus DACR 5, the overall significance have gone to 4.2 sigma, but the overall nature remains the same. It is that the error bar shrink a little based on the more data. So that seems to be robust, but at the same time, I hope I have told you a little bit about how to interpret these things, but I also want to tell you as the next thing, given I've showed you the results already, what are the things you might not need to think about if you want to measure it or if you want to look at the robustness of a result like this. Fundamentally, if you can measure how the expansion rate of the universe or the scale factor evolves as a function of time in this homogeneous and isotropic metric, then that is what you are interested in, and that will answer all of your question about dark energy or its nature. It has also sensitivity to curvature and neutrino mass. But how do you measure A of t? So scale factor of the universe, if you want to measure its evolution, then one of the key thing which can help is spectroscopy, which is why there is a spectroscopic instrument. So just for people who may not be familiar with spectroscopy, what we are really talking about is that, as all of us aware from fundamental physics, the light as a function of wavelength also appear as different frequency and hence also appear as different color as shown in this plot. And so when the lights from distant galaxy get emitted, they experience many different effects. One of these effects is that they have to climb out the potential well of the dark matter halo, which is shown by this curvature. And so they will get shifted. A monochromatic light wavelength is going to get shifted as it's climbed the potential well. But then once it's in the free space, it's going through the universe between the observer, so us, and the galaxy. And all of this is going through the expanding universe. And so because of the expansion, the wavelength gets stretched, and this is what we call cosmological expansion. So as the light travels from the source, there will be terms like gravitational redshift and as well as cosmological expansion. And so you can measure this shift in the wavelength, which is what you're interested in. If you see any feature in the spectral distribution energy of the line, so for example, O2 flux, what you'll find is that for different galaxy, it is a different location, and you can measure what is the shifted wavelength location based on our expectation from quantum mechanics of that particular line, emission or absorption. And then that will give you this quantity redshift. So we can define redshift as essentially shift observed in this kind of features divided by the emission wavelength, which we already know. If you know the feature properly, that will give you redshift. And then redshift is connected to the scale factor A of t, which I've been talking about so far as 1/1 plus z. So you can measure pretty much for all of these galaxies. We have 14 million galaxies. For each one of them, we have a scale factor or redshift, right? But what we don't know individually is what is the time of emission. If we knew time of emission, we know the full function, but that's the hard part. Since you don't know the time of emission, we need to figure out alternative ways to figure out when these lights were emitted. And unfortunately, that cannot be done on the individual object basis. So we can measure redshift individually, we can estimate scale factor individually, but we cannot measure T of E individually. And so we have to do something more complicated and something statistical. If you want to visualize this in terms of different kind of spectra, so these are real spectra observed from DESI, average over few sources to make it look more smoother than what true observation is for individual galaxy. And you can see there are many features in these spectra. So these, the y-axis is look back time, x-axis is wavelength. And you can see there are many features in the spectra. If you can look at, for example, the green line, these are O2 emission line from a star-forming galaxy. And if I were to plot a model for one of these features, for example, this O2 line as a function of redshift, so in lambda CDM, the white solid line is the expected shift in this feature as a function of look back time, whereas the dash line, white dash line, is what will be the prediction in W0 WCDM, which is the best fit DESI result on this thing. And so the issue, again, if to put it another way, we know all these spectra, we know these features and their location, but we don't know what is the y-axis location of these spectra. And so we don't know the look back time or the time of emission. And that's what we need to figure out an alternate way to estimate that time of emission for each of these spectra. So one way to do this is by measuring distances. So we can measure proper distances of this object, which will be given by the integral over 1/a of t. That's the expansion, that's the scale factor as a function of time, multiplied by all the light is traveling with speed of light, so c. And so if we can measure, let's say, this distance, and if there are things, what you can imagine as a standard candle, which means we already know from some other physics how much light is emitted from these objects. So these are luminosity, total luminosity of the objects. And so we already know the value, and that's why it is standard, standard candle. You can actually work out how the flux is going to change as a function of distance. So flux is going to be L over 4 pi dl square. That's the surface on which light is spread. And so this is what is called luminosity distance. And luminosity distance will be related to physical distance by a factor of 1 plus z because of this additional stretching of the wavelength and difference in photon arrival and emission time between a pair of photon. And so if you account for all of this factor, what you'll find is that if you can measure a standard luminosity of the standard candles, you should be able to measure luminosity distance, and that will give you an integral of 1/a of t from t to t naught, so time emission to t naught. So this is an indirect estimate of emission time. And so this is what is also known as supernova cosmology, or a standardizable candle, which is close to standard, but not exactly standard, which is where most of the messy physics in and the challenge is. If you can measure that, then that will give you one way to measure A of t. Another way to measure A of t is through baryon-acoustic oscillation, BAO. So if you can imagine that in the early universe, different components like dark matter, gas, photon, and neutrino were all coupled, and then there was a perturbation. As the universes start to expand, the photon and gas plasma, blue and red line, were together, and they were dragged. Photon dragged the baryon with it. And at some point, when the universe is cold enough, that got decoupled, and so the photon were left baryon at some particular scale, where we see slight excess probability of matter as well as baryon. And so we see this excess in galaxy correlation and pretty much everything in large scale structure. Now, this scale is, because we know this scale, we can predict this scale based on measurement from early universe. This becomes what we call a standard ruler, or and then this scale is known as RD, Sound Horizon, which is essentially the integral of sound speed in that plasma scale by the rate of change of scale factor h of z, which I have already defined the Hubble rate. And so if you know the standard ruler, let's say a size of a particular feature like BAO, then again you can measure distances by essentially using simple geometry. If you know the scale, then the angular scale made by the BAO will be related to the angular diameter distance. And angular diameter distance is related to the physical distance because of, again, the effects of the fact that things are going to stretch, and there's a difference in time when these things get emitted versus when you actually observe them. And so this DA is called angular diameter distance, which you can measure using BAO by looking at large scale structure or galaxy survey. And you can measure also BAO not just perpendicular to the line of sight, but you can also measure parallel to the line of sight, which is in terms of the redshift, what is the size of BAO, and that will give you the local Hubble rate at the local redshift of these galaxies. So BAO is essentially helps you extract ratios of, so what is the standard length of this ruler, RD, ratio of that to the perpendicular distance of these things in the sky, as well as parallel along the line of sight DH of Z. And you can also think about isotropic term part of the BAO, which we call DV of Z, which is essentially combination of perpendicular and parallel BAO scale. So how do you BAO? Yes.
5 minutes.
Sure, thanks. So how do you measure BAO? One way to measure BAO is by looking at two-point correlation function. So you can do galaxy survey and essentially look at count how many pair of galaxy you find as a function of distance, and do that in your entire volume. And then compare that to uniformly distributed random in the same volume. So pair of random, this will give you, so if you have pair of galaxy as a function of distance and pair of random as a function of distance, you subtract -1. What this gives you is the excess probability of finding a pair of galaxy as a function of distance compared to a randomly distributed universe. And if you are to measure that kind of thing, you'll see this red points, which shows this BA scale again. And so being able to measure the location at which you see this excess probability allow you to measure delta R BAO. And so this is data from EBOS, where we have about 2% measurement of BAO. So that will allow you to measure time of emission in an integrated way. So if you want to do this kind of exercise, what you would like to do is you want to measure many galaxies for them, position of these galaxies on the sky, as well as redshift, so RADEC and redshift, which will allow you to do this calculation of pair count, and hence allow you to measure two-point correlation function and determine BA scale. And once you have the BA scale, you can use it as a standard ruler, as I described earlier. Now, how do you can actually do this in Fourier space, so rather than in place of doing two-point correlation function, you can grid your galaxy density field and correlate the Fourier transform of your density field in real space, delta KK, and this is what is called power spectrum. And so this peak in correlation function will appear as oscillation in power spectrum. And by looking at the scale of this oscillation, which you can see even in real data, it's very subtle and tiny oscillation, you can figure out what the location of BAO is. And so the analysis typically is done in both spaces, Fourier space and configuration space. So just to summarize what I've talked about so far is that there are different fundamental applications or fundamental postulates of what are the kind of things exist in the universe. Many of these things are connected to in the context of dark energy equation of state and its evolution as a function of redshift, which essentially is connected to what is the scale factor as a function of time, which you can measure if you can measure what is the distance as a function of redshift, dp of z. And then you can measure dp of z either through a supernova or BEO. Now, the question is, how do you improve the precision of measurement of BEO? Because I'm talking about in the context of galaxy survey, that's where I'm going to focus. And so if you want to measure, improve the precision, a natural thing is to measure many galaxies as you can. So I'll go through this a bit quicker since I don't have too much time. But I hope you'll get the essence. So if you want to do this, you can do a photometric survey like DESI legacy imaging survey, which can give you of the order of 1.5 billion galaxies and 1.3 billion stars, where there are images, but you need spectra to measure BEO. And so you can make an instrument like DESI with 5,000 fibers. And so if you have an instrument like DESI, if you observe 8 hours per night, you observe two of those observations, a 30-minute exposure time, you'll measure 64,000 spectra per night. And in 5 years, you'll measure something like 58 million spectra with 50% efficiency. So this is the kind of number DESI is working with. DESI is expected to observe something like 40 million spectra in 5 years. But you notice the 58 million is just 4% of the total number of galaxies you'll see at this kind of depth. And so you need to be very careful about which 4% of galaxy you want to select to be able to measure dark energy equation of state as precisely as possible. So how do you go about measuring for this very precisely? The main thing is that you need to figure out how the signal to noise scale for something like BEO. And so signal to noise has two quantity. One is the volume, how big the volume you're observing in the survey. Another is short noise, what is the sampling rate you are performing these measurements with. And so you want to minimize the short noise such that the short noise effect is basically negligible compared to the amplitude of the power spectrum itself. And then you want to maximize the volume to do this. And so if you actually do this exercise in general, what you get is the n times p, number density of galaxy times amplitude of the power spectrum should be close to 1. And then that will give you the ideal condition. So this is the noise estimate for BEO, what the percentage error looks like as a function of redshift. The white line is best possible noise estimate given the volume exists. And the red line is what DESI hope to achieve as it approaches its 5-year survey. So DESI is a 5-year mission, which is a 4-meter telescope. It is a spectroscopic survey which has a focal plane of 5,000 robots, and it observes 5,000 experiments at a time, compared to previous experiment where you had to manually plug in optical fiber like SDSS to do this kind of thing. So I'll skip this in the interest of time, and maybe I'll go to the more important thing where I just want to come back to the results I showed you in like last 1 minute. So the BEO will allow you to, galaxy survey like DESI will allow you to measure correlation function as a function of redshift. So these are the correlation function. And each time you can see the BEO peak, you can estimate what is the location of this BEO peak. And if you put that in the context of cosmology, you'll get these points, which is essentially the measurement of BEO peak divided by what is the lambda CDM expectation. And the dashed line shows what is the W0 W CDM best fit model. And so you see there is a hint of deviation of this DOP compared to the solid line, which is the lambda CDM prediction. And this is what this signature is. You can look at this same result in various different planes. You can look at in W0 W parameterization. And what you'll find is that just DESI plus CMB will give you something like 3 sigma results, which is very interesting without any supernova. And if you combine that with supernova, something like DES, you'll get 4.2 sigma results in this kind of plane. And if you don't want to work with supernova, you can also try to do this with weak lensing, and that will give you this orange contour, which is much bigger, but then in the same space. And so our results are a bit robust, independent of what experiments you combine with. So with that, I will leave you with this slide where I'm showing you what these results looks like once you do the 5-year of DESI survey, which is shown in this magenta line. So that's 5 years of DESI survey with CMB and supernova. if the evolving nature of dark energy stays at the same location, this will be, say, quite significant result compared to now. And that is shown by this magenta curve, which is not far in the future. By 2026 summer, next year summer, we'll have 5 years of data, and probably in another year, by 2027 summer, we should have the results released from this 5-year data, and we'll see what happens to this interesting signal, which is 3 to 4 sigma now, whether it becomes 5 sigma or whether it stays at the same level. And so we are really looking forward to what happens in the near future. Thank you.
Thank you, Dr. Shadab, for the nice talk. I have a request. Let us shift the question and answer session during the final discussion session. And may I request Dr. Shadab to stay up to during the discussion session? Okay.
Sure. Yeah.
Okay. Our next speaker is Adrian Adame from Autonomous University of Madrid. Can you please share your screen?
Yeah. Can you hear me well?
Yes, we can.
Okay. Perfect. So can you see the presentation?
Yes, maybe change one slide.
Yeah.
Yeah, it is. It's fine. So
Perfect.
the screen is yours.
Perfect. So thank you very much for inviting me for presenting the DESI 2024 results about the full shape analysis. So I wanted to start presenting what are the year 1 galaxy samples. So the final DESI survey will last 5 years, as the Shadab has already presented, and we split the targets into the dark time, which is when the full moon is less than half illumination, and the bright time when we only target like the BGS. So here I can show the total footprint and the expected footprint of the DESI survey. And here what I'm showing is the fraction of the final coverage, what in the year 1 is included. The full footprint will occupy like 14 degrees square, which is about 1/3 of the total fraction of the sky. And in DESI, we are using 4 targets or 4 tracers of the large scale structure of the universe, which is this bright galaxy sample, which are all the observed during the bright time. And then these are the dark time objects, which are the luminous root galaxies, the mission line galaxies, and quasi-stellar objects or quasars. I wanted to show these pictures, which are extracted from the DESI Legacy Survey DR9, which is being used in order to make the target selection, because as Shadab has previously said, we cannot observe with the DESI fibers every single object that we have in the photometry. So in order to have a sense on what are we referring when we say LRGs or ELGs, well, this is actually the objects. So here I just put some rough numbers, which encompasses the first year of data and how much fraction of area it's covered by these different tracers. So for example, for the quasars, we are covering like 7,000 degrees in the sky. And also I saw here the redshift ranges. For example, the LRG is covered from 0.4 to 1.1 in redshift. Emission-like galaxies are higher redshift, and the largest redshift targets that we are using in the dark time analysis are the quasars, which ranges from 0.8 up to 3.5 if we include also the Lyman alpha tracers. Also, I wanted to show these. These are the pictures of the completeness of the survey on how many passages we have been doing in each patch of the sky. Because what we are doing is like for every single object that we have selected to be observed, we are taking in the dark time 7 spectra. And for the bright galaxy sample, we are taking 5 because they are closer and the signal to noise ratio are way higher. So this is actually the data that we have for the year 1 sample. Recently, we have published the DR2 PAO analysis where they include much more galaxies or all these types. So as I wanted to comment about the DESI GR1 full shape analysis, these are the actual galaxies that we are using for this analysis. And here, what I'm showing here is how is the distribution in redshift of all these targets for the BGS, which are the low redshift sample, the LRGs. There are some overlap in the ELGs and LRGs that we can use for do some cross correlation, and also the quasar, which are the lower number density targets. So one important thing that I want to emphasize is that all the analysis within the DESI collaboration has been done blindly. This is mainly aimed to avoid confirmation bias when we extract the cosmological parameters, in order to, just to avoid this confirmation bias, as we know the result from other collaborations. So what is new in DESI is that we are doing this blinding at the catalog level, which that means that we take the coordinates that we measure from the galaxies in the survey, the rate ascension, declination, and redshift, and we use a blind cosmology. We don't know what the cosmological parameters is, in order to convert this rate ascension, declination, and redshift into basically a distance, the radial distance. And then we use the fiducial cosmology for our analysis to convert these positions again to redshift declination, and this redshift is altered by this change in the blinding. This also, this what gives us is a blinding in the Alcock-Paczynski parameters, which are used basically for the BAO. But when we use also the full shape of the power spectrum, as I will comment in a few, we are also sensitive to the amplitude, to the overall amplitude of the power spectrum, and also the redshift space distortions. So in order to that, we have to include also these other new terms in order to be blind also to those parameters. Also for the primordial Gaussianity analysis, we use a set of weights in order to blind also for the PNG signal, that I can comment later if you're interested. Overall, apart from this blind pipeline, within the DESI collaboration, a lot of people have been working on validating all the analysis and testing for all kind of possible systematic errors that can be arising in the observation. The first one are the theoretical frameworks. We know that our modeling doesn't work up to the smaller scales that we can actually prove with the survey. So we can compare the different modeling up to the K-max that we use for the analysis, which is 0.2. And we find that there is no difference or no statistical difference between these different modelings. And then we can also model the different imaging systematics. We can check how these templates that we use in order to remove these imaging systematics in the observing, due to the observing conditions, how affect to the different tracers, the spectroscopic in the determination of the redshift of the galaxy. Also, it's very important, this fiber assignment systematics, because as I saw in the previous slides, in the focal plane, we have to point the optical fibers that take the spectra. So maybe the two galaxies are too close and this fiber can collide, and this induces some errors. So we can take all of this into account. Also, when we are testing all these pipelines, we have to generate mock catalogs using simulations, and also this way to prescribe to establish the connection between the galaxies and the simulation can induce some systematics, but we can also take into account how much this can change the cosmological parameters, also the fiducial cosmology and the covariances. Overall, all these account to 0.4 or 0.5 sigma in quantities of the statistical errors that we have in DESI. So we add this systematic error to the final constraints. Also, as we have basically a large catalog of galaxies, how we can extract the cosmological parameters from this. So what is been doing is pretty standard, is to compress all this information in the catalogs into 2-point statistics or even higher point statistics. But in this analysis, we only stay at the 2-point level, which is basically the 2-point correlation function, which is basically counting pairs as a function of the distance. And here is an example for the emission line galaxies in this redshift range. And we use the Landis-Luss estimator And in Fourier space, the Fourier transform of this two-point correlation function is the power spectrum, where we are using this estimator. And here you can see the power spectrum for this galaxy sample. So now I want to talk about the full shape analysis and the cosmological constraints that we can infer from this of the year one DESI survey. And I wanted to start to establish how we can extract cosmological information from the spectroscopic surveys. So the very first step is typically to compress all this information that we have in the redshift and the positions of the galaxies into some summary statistics, which, as I have already presented, typically are the two-point correlation function or just the power spectrum. From here, we can just take one more step and just from the two-point correlation function establish where the peak of the BAO arises, and we can measure from this these cosmological parameters, which is basically the distance, the different distances to those BAO peaks. But we can also try to fit not only where the position of the BAO arises, but also the amplitude of the overall amplitude of this power spectrum or two-point correlation function. From here, we can use this modeling, which is called ShapeFit, where we have a template for the power spectrum or the two-point correlation function in terms of some cosmological parameters as these BAO positions, and also the amplitude of the growth, the residual space distortion, and we can tune some parameters in order to fit the data. And from these parameters, we can extract again the cosmological parameters, or we can just go full modeling analysis, which basically means that we assume lambda CDM or your favorite cosmological model with the parameters that arises from those cosmological model and get the full pipeline down to the power spectrum on all the two-point correlation function. So here is summarized in a table what I basically have said, that with the BAO fits, we are only fitting the position of the BAOs with the RSD fit, which is similar to what we can also take into account the amplitude of the power spectrum. And this full modeling where we just model from first principles, assuming our favorite cosmological model, the full shape of the power spectrum. Every model has its own advantages. So some of them are only sensitive to some parameters, but are way simpler and cheaper to run, while the others are sensitive to all the cosmological parameters, but you have to run all the pipeline to compute the power spectrum for each model that you want to test. Here, when I present what is done in the full in the ShapeFit modeling, where you have a template for your linear power spectrum, and you add these terms that allow you to basically to tilt the power spectrum in order to get a better fit, and also modulate the amplitude of this power spectrum. These nuisance parameters that you have introduced in this ShapeFit, like M and N, can be translated into the cosmological parameters, which at the end of the day is the quantity you are interested in. For example, sigma 8 and S8 are related with these M and N parameters via these relations. And here I just wanted to show how these N and M parameters for a fixed M, or in this case, or for a fixed N, in this case, change the template that you have for the power spectrum. But in the full modeling, what we take is just we know the EFT of LSS, the effective field theory for the large scale structure, and we start from a bias expansion. This means that I want to relate the underlying matter distribution, which is at the end of the day what I can predict with the EFT modeling, with the observed density over density of field of galaxies. So typically a linear order, you can just take these terms, but in perturbation theory, you are allowed also to include all these other terms, which these are nuisance parameters that you want to marginalize over when extracting the cosmological information. So at the end of the day, the power spectrum that you want or you are measuring can be modeled at this way, where all these terms arises from this bias expansion and are the perturbation theory information that you can extract. But also, as we don't know how the physics of the very small scales work, we can try to marginalize over all those scales. And we can also take into account how these small scales affect to the largest ones. So these are these EFT counterterms. And also we can introduce one stochastic term. And here, just for illustration, I want to show in black is the linear power spectrum that you usually get for CAM, assuming some cosmological parameters. And here are the different terms that appear in this equation. This I delta square, for example, are this red line that appear here. In addition to this, we have to model also other effects, as the IRs mentioned, the Alcock-Paczynski effect that arises from assuming a fiducial cosmology, which is not the same as the underlying one, the multiple decomposition, etc. So it's a very complex modeling, but it can be done. And within DESI, we have considered for different codes, which implements this basically this modeling in slightly different ways, in order to cross-validate the predictions if they are consistent between each other and if we can extract the same conclusion from them. These codes are Velocileptor, SOGNU, PyBert, and EFT GSM. This LPT and EPT means that once what I have shown previously is the Eulerian perturbation theory, but you can also do this in Lagrangian coordinates. So the equations change a bit, but the cosmological conclusion must be the same. So first of all, what we have done is to compare these codes if they are consistent between each other, and from a mock challenge, basically in a simulation where we do know exactly what are the constraints that we are, the cosmological parameters that we are inputting. Let's see if we can recover the same constraints, and indeed we can do it. Also, you can do this for the real data, and you see that regardless the codes you are using, you recover the same cosmological parameters and the same contours. And also in this other plot, what I wanted to show is that this shape fit, which is more simpler conceptually than this full modeling, also gives a very consistent constraints compared to the full modeling of this or the power spectrum. Finally, I wanted to display some of the priors of the parameters that have been used for this full shape full modeling approach, where basically we set like uniform priors, which are very non-informative priors, except for omega baryon and the scalar index, which came from the CMB experiments, and you need them in order to get like constraints from that. And also, before doing this, as I said, up to this point, we have been working only on the blinded catalogs, where we don't know what exactly, well, we have shifted the underlying cosmology to some number that we are not sure about them. And we wanted to test all the analysis variations that we came up and see if we recover consistent results between all these. And what you can see here is that basically all the constraints are consistent under these analysis variations, instead of using some covariances from MOX or analyzing the North Galactic Cap separately from the South Galactic Cap, etc. Everything seems consistent. So once we have the analysis pipeline and we are pretty sure that everything works fine, we can try to extract the cosmological parameters from the DESI. So first of all, we can test the lambda CDM cosmology, and using DESI only data. So we have the BEO analysis. We can test the growth of the structure, and also we have now the full modeling, which allows you to test also the redshift space distortions, and from that you can measure also the amplitude of the power spectrum. So here you can constrain omega matter combined with sigma 8 for the different samples, and you can also combine all the different tracers that we have within DESI and get this tight constraint on omega matter and sigma 8. Similarly, you can do this for the H0 using a prior on the BPN, on the omega baryon and the scalar index, and these are the numbers that we recover. So interestingly, what we see is that the values for sigma 8 or S8, which is just a combination of omega matter and sigma 8, we recover a value which is basically on top of the CMB measurement of sigma 8, and a bit in tension with this weak lensing analysis, which proved much later much different scales. So the DESI analysis is more in agreement with this sigma 8 from the CMB. Now we can also combine DESI with other proofs, such as the CMB experiments and DSY3 weak lensing analysis, in order to get the tighter constraints of these parameters, as they are proving different regions of the parameter space. And here is what we find. This it's not compatible with the CMB, of course. And these are the corner plots. So this is just for the baseline lambda CDM analysis. So we can also test to try extensions of the lambda CDM paradigm. And one of the models that we have tested is WA testing for dark energy in light of the results that we obtained in the GR1 PAO analysis. In that sense, this full shape is not adding that much, since the growth this WA affects more to the background expansion, and this is mostly proved by the PAO analysis. However, we can tighten slightly more the constraints, and by combining with CMB and different supernova samples, we get different hints from a deviation from the lambda CDM that are not equal to 1 and WA equal to 0. This is particularly significant for this supernova with DS supernova GR5, which the tension with lambda CDM goes up to 3.8 sigma. Also, by combining this within this framework, we get like a slightly different constraints compared in the other cosmological parameters compared with lambda CDM. As you can see here, that depending on the supernova sample that you are using, you shift slightly the value of omega matter, but everything remains consistent with what we have up to now. Other thing that we can prove with the full shape analysis is the neutrino masses. The neutrino masses, the free streaming of these neutrinos, basically in the late universe allows you to suppress the structure formation on very small scales, and this can be seen as a suppression in the amplitude of the power spectrum. Here, for what we show is how it changes the amplitude of the power spectrum for various values of the sum of the neutrino masses. And here in the gray shade area is the scales that we are testing. So it's an effect that can account up to a few %, and in principle, and we can measure this properly in the full shape analysis. So here what I am presenting is the constraints that we have. We need a tight prior with the scalar index because this effect is very degenerate with the field of the... So NS is the amplitude is the tilt of the primordial power spectrum, and this is very degenerate with the sum of the neutrino masses. So we have to put a prior measure from the CMB basically, which is, and 10 S10 means that is the 10 times the width of the prior, and we are able to constrain a lot the scalar index of the sum of the neutrino masses, right? So this raises some issues that if we allow, well, this is the posterior of the distribution that we get for the sum of the neutrino masses, and what we find is that it is, when combining with the CMB, this favors very low masses of the sum of the neutrino masses. But well, here this region is what we find, what you would expect if you have the normal hierarchy of the neutrino masses, and this is the inverted hierarchy. So this seems that pointing that DESI is favoring, like in this sense, like the normal hierarchy of the neutrino masses. However, if we allow to constrain also the not WA for the dynamical energy, these constraints are much wider, so we are not in the point of affirming that we have one or different hierarchies of the neutrino masses. Also, it's interesting to say that here, around here lies the constraint from the ground-based experiments of the sum of the neutrino masses from the oscillation of the neutrinos. And also we can constrain the N effective from the CMB or from DESI, and this is the result that we find, which is in agreement with the standard model of the particle physics for the N effective. Also, as we are now able to constrain the graph of the structure, how it's changed the F sigma 8 factor, we can also test different models of modified gravity that affects precisely how the structure grows in the dynamics. So in principle, in modified theories of gravity, you can change this relation of the Poisson equations by this mu and sigma function that at first order can be parameterized in terms of this mu naught and sigma naught. From DESI, we are not able to constrain this sigma naught. So basically, these sigma naught constraints come only from the CMB.
I will do today, don't make.
But
this I'll make I'll eat the yogurt without milk. I have plenty of this.
But we can also constrain, but we are able to constrain pretty much this mu naught. And what we find is that this value is pretty consistent with what GR is telling us. Here you can see the constraints. And this apparent tension that appears for sigma naught is only driven by the CMB. So maybe we need a better understanding of this, but this is what we have up to this point. And finally, the last model that we have been working on within DESI is primordial non-Gaussianity.
5 minutes.
Yeah, perfect. So basically, during inflation, there are single field inflation predicts that the spectrum of perturbations is nearly Gaussian, but some exotic models like multi-field inflation may allow you to deviate from this Gaussianity in the amplitude of the initial perturbations. We can prove this because there is a very interesting effect, which is the scale-dependent bias, is that when you have this primordial non-Gaussianity, this is the matter power spectrum, and this is the power spectrum that you should measure in case there is a Gaussian standard initial conditions. But in presence of primordial non-Gaussianity, this bias, it appears a new term proportional to this p phi and the amplitude of these non-Gaussianities that increase the signal with 1 over k squared at the very large scales. Here you can see this basically this term that arises with in presence of local PNG. So in principle, we can look for this signal in the power spectrum of the tracers in the quasars and LRGs, which are expected to be the best tracers. They are higher redshift and they are proving larger volumes. And this effect goes, as I said, with 1 over k squared. And these are the results that we find. So for the LRGs, we can is everything consistent with still with zero. So in principle, there is no evidence for this primordial non-Gaussianity. And if we combine also with the quasars, we get like this 1.7 plus minus 8, basically. Here are the posteriors of this thing. And this represents like a 2 times improvement compared to Evo's analysis of the large scale structure. We are not yet comparable with the Planck analysis of the CMB, where you can also measure this abundance of the primordial non-Gaussianity. But there are forecasts that for GR5 DESI, we can reach that level of accuracy. So as a take-home messages, I want to finish my presentation is that adding this full shape information to BAO allows you to be sensitive to the structural growth of the matter during the evolution of the universe. The results that we extract from here is that the sigma 8 is compatible with Planck, like pointing that there is no sigma 8 tension in that sense. We find a 3.8 sigma preference for the dynamical dark energy when combine the DESI full shape analysis with the BAO analysis in year 1 plus the supernova samples. We still find a low neutrino masses. And this is alleviated when you are allowing for a more flexible model for the dark energy. And as I said, the FNL constraints have been improved like a factor of 2 compared to previous LSS analysis. And we expect to reach plan accuracy by year 5. And stay tuned because the year 3 full chip analysis are coming during this year probably. Thank you very much.
Okay, thank you for the nice talk. If there is any urgent question, we can ask the audience, or else we can leave the question answer to the panel discussion session. Okay, so let's move on to the next speaker of the day. Alessio, are you there?
Yes, I'm here. Hello.
So
Can you
let's
hear me?
begin. Yes.
So let me see if I can share.
Okay, we can see the screen, but maybe full screen.
I try full screen.
Sorry.
Is
Yes.
it full screen now? Yes.
Yes. So today's last speaker is Alessio Notari from University of Barcelona, and he's going to talk about dark radiation, varying dark energy, and neutrinos with DESI baryon acoustic oscillation.
Okay. Thanks a lot for the invitation for this workshop. So I try to give us just a few remarks on several aspects, several consequences of DESI BAO measurements. So let me go quickly on the basics, which have been already explained. But let me focus on the sound horizon at recombination. I call it RD. And now this is simply our distance ruler for BAO measurements. And it's simply the distance that a sound wave can travel from Big Bang to decoupling. And as you see, it depends on the speed of sound and on Hubble parameter. Now, as we know very well, this is a standard ruler that today corresponds to 150 megaparsec, more or less, scale. And then by looking at CMB or BAO, we can measure the angle that corresponds to this scale. Okay, and simply just by a triangle, just by geometrical relation, we see that the angle that we measure, for instance, the first peak of the CMB, is the sound horizon over the distance. Okay, and that's a way that we have to measure distances at a given redshift. Of course, this can be used also in galaxy correlations, not only in the CMB, and that's precisely the BAO measurement. So in galaxy correlation, we measure some angle also, which gives you, again, a ratio between RD and a distance at a different redshift. Okay, so the fundamental scale is RD here, but there is also, of course, another way to measure distances in cosmology, which is supernovae. In this case, we measure luminosities, and by comparing the intrinsic over the observed luminosity, we can infer the distance. Of course, we are assuming that all supernovae of a given type, in this case type 1a, have the same intrinsic luminosity or can be standardized to this. And then from this type of distance, we just relate to the other distance by a factor of redshift. So they are essentially the same thing. Now, a very important distinction, we can use supernovae which are uncalibrated, or we can use supernovae which are calibrated. Now, this means simply that in the uncalibrated case, we don't know what is the intrinsic luminosity. And therefore, we cannot measure the overall constant, which is in front of the distance. Or in other words, in a log scale, we cannot measure this additive constant. And the reason is that it depends on the intrinsic luminosity. And so for the same reason, we cannot measure H naught if they are uncalibrated, because in this constant is a combination of the intrinsic luminosity and H naught. Okay, so that's just a preliminary thing, as you know very well. Now, if you combine BAO, CMB, and uncalibrated supernova, you can establish the lambda CDM cosmological model, or maybe a deviation from it. However, we are going to see what happens now with the DESI data. So these are year one DESI BAO data. These are different points of the distance, as we have seen already. And the most relevant features are that, well, first of all, we can see by eye that there was a data point which was low at this redshift, which was about 3 sigma discrepant with previous BAO measurements. Then let me also stress that, however, the DESI seems instead consistent with another BAO measurement, which is given by the DES collaboration, the Dark Energy Survey, which is different from DESI, okay? And this is this blue point here. So, and the overall feature that you can see, so let's say by eye, is that DESI, which is black, and DES, which is blue, they are all consistently lower than SDSS, which is kind of higher almost everywhere. And so, as a consequence, DESI and DES, they prefer smaller distances, which means higher H0. This is a generic feature. Okay, this is confirmed also in the new DR2 data. You can see that this is DR1, this is DR2 in solid, and the points have smaller error bars. They have moved a little bit, but overall the same behavior remains. By the way, the discrepancy with the previous SDSS data is now reduced from 3 sigma to 2.6, but it's still there. Okay, it's less significant. It's this point here. I'm talking about only about this point. Okay? And then, but the overall feature is that smaller distances, so higher H0. Now, we can combine now data with CMB and Supernovae to extract parameters, and I will consider this baseline set Planck, either Supernovae from Pantheon or from DES, and then DESI BAO. And then I will compare with local measurements of H0 because I want to know if there is anything that we can say about the H0 tension. So another thing that I can do is also to change the Planck likelihood, because from Planck 18, there are also Planck 2020 likelihoods. And in particular, I will focus on the one called Hilly-Pop, Lollipop. Okay, so these are my data. And then the question I want to answer are two types of questions. So first of all, let's try to see if we can say something about the H0 tension. Is there a model that can address the H0 tension? Now, in this paper, we have shown that with DESI data, if we invoke some new physics at early time in the form of dark radiation, this is a possible way to address the Hubble tension. What about new DESI data? Well, in DESI DR2, we have not performed yet a full analysis, but things are almost the same. Okay, they didn't change much. However, there is a big caveat because there was a new data release from in the CMB, so from the Adame experiment. This was also a few weeks ago. And actually, this seems to rule out this possibility of dark radiation. So I will show it quickly. Then instead, we can also just keep the standard view of neglecting the shoes measurement. We neglect it. And then the more like conservative view, if you want. And then in this case, I want to think a little bit about what is the preference for time varying dark energy, as has been stressed in the previous talks. Okay. So H0 tension, as you know, is a tension between a local calibrated supernovae and all other combinations. And this tension is about 5 sigma, okay, nowadays in the lambda CDM model. So either some measurement is wrong, such as shoes or maybe the other ones, or the model is wrong, okay? This lambda CDM model is wrong. So we reassessed essentially the status of the tension in dark radiation models. So what we get is the following situation. Dark radiation changes the Hubble parameter in the early universe. Therefore, it changes RD. That's the main effect. And today is almost negligible. So it's a good way to change just RD. And there are many candidates. I will not go through for dark radiation, like extra neutrinos, extra axions, and so on. Indeed, the parameterization is in the parameter n effective, like an effective number of extra neutrino species. And in standard model gives about 3, and new physics gives something more than 3. So we consider a prior of delta n effective positive, because we assume the standard model to be true. And then there are actually two types of dark radiation which can be discussed, two simple types. One is free streaming, non-interacting, completely non-interacting. And the other one is when dark radiation forms a perfect fluid, such as similar to the photon baryon fluid. So it has some fast self-interactions and it forms a fluid. Okay. And then to be more precise, there are, and very importantly, there are more effects on CMB fluctuation. It's not just changing RD, but we are also changing the damping scale of the CMB at large K, at large momenta. And we are also, in the case of free streaming, we are also adding a shift to the peaks of the CMB. It's called the phase shift, but it's not present in the fluid case. Okay, so constraints before DESI were pretty, well, relevant. Let's say that there was no indication for any delta N effective. And you see that the upper bound is around 0.3, 0.4. This is with pre-DESI data. When we add DESI instead, we see that there is some preference. So these are the new lines with DESI, blue solid and orange solid. Especially for the fluid case, there is a preference for a non-zero delta N effective. Although it's not a very strong preference, but it's a little bit more than 1 sigma. And this is quite interesting. However, there is also BBN constraints, as we all know. So BBN, they constrain this possibility of having a large delta N effective. Indeed, when you combine with BBN, you get just an upper bound. Okay. 0.3 and 0.37. However, one can think of a very simple model where BBN, where dark radiation is not present at BBN, but is produced after BBN, but still before recombination. So indeed, for example, if you have a massive particle that decays into dark radiation, in that case, you do not apply constraints from BBN. And so we can consider actually 4 cases: free streaming present before or after BBN, and fluid present before or after BBN. So this slide shows the result. We also, by the way, used more recent, as I said, Planck likelihood, which is called the Hilly-Pop, which is interesting for 2 things. So first of all, it has a bit larger sky fraction, but also the so-called A-lens anomaly is not present in this likelihood. And so it's resolved. And these are the results. I show the level of tension for H in the H0 tension for different models and for different data sets. In particular, you can see that with DESI, which is orange and green, H0 tension is reduced for all models, and this is true because DESI, as I said, prefers a slightly higher H0. But in particular, for the fluid dark radiation, we get a tension which is below 2 sigma, especially when we use this Hilly-Pop likelihood. This is quite interesting. And then one can even combine with the local measurement of H0 and find that, yeah, there is evidence for a non-zero and effective. And this evidence is actually pretty large. It's like 5 sigma evidence. And indeed, the chi-square of the full fit is improved by a very large amount, like -25. Okay. However, so let me skip to this. However, as I said, a few weeks ago, new measurement from ACT came out. ACT is measuring TT spectra, which is in this first plot, but also polarization with very good accuracy, very good precision, sorry, at large L. So Planck in comparison goes only up to 2000. Errors are very large here, but ACT goes to higher L. And the new results is that ACT is ruling out this possibility of dark radiation. And the reason is that in the damping tail of the CMB, ACT is observing excess power, so too much power. And so this is not compatible with dark radiation. Dark radiation is actually giving more damping. Okay? And you can see that the constraint is very different. This was the Planck curve, and this is the ACT curve, so it's pretty strong. And actually, interestingly, ACT is preferring a number of neutrinos which is less than 3. The central value is 2.8. So it's not really that ACT has improved dramatically the error bar, but the central value has shifted to less than 3. And therefore, the possibility of having large and effective is like of having, for example, 0.4 is statistically very, very, very small. Okay, but this interestingly will be also double checked by SPT, which is also measuring the same thing very soon. So that's the chapter about dark radiation. Now let me go to dark energy. We have already seen this in the previous talks, and I will try to highlight a few things. First of all, now forget completely about the Hubble tension, okay? I'm just talking about standard uncalibrated supernovae and DESI and Planck. So as you know, a generic fluid has an equation of state, which is, has a continuity equation, which looks like this. So standard assumption in particle physics and field theory is that W is less than -1, larger than -1. You can see immediately from this equation that if that W is less than -1, then when the universe expands, rho is growing, so which is completely counterintuitive, right? It's called a phantom behavior. So you expand the box and the energy density, instead of being diluted, grows. Okay, so we actually don't, so in general, we don't want such a behavior, okay, because it's very hard to obtain it from a reasonable field theory model. Okay, so however, the standard parametrization is just a parametrization, the CPL or W0WA, which does not take this into account. So it allows to go below -1, this parametrization. And as you know, lambda CDM is disfavored when you allow for this parametrization at about 4 sigma when combining with DES supernova. But is this really evidence for W less than -1 in the past? I think this is a relevant question. So this is just a plot of the fit. So we tried to highlight a few things. First of all, actually this preference, let me stress, it's not only in DESI data, but we also found that even if you replace completely DESI data, you forget DESI, and you put the DES BAO data, then you still find the 3 sigma lambda CDM disfavored at 3 sigma, which is pretty large, even with the without DESI. Okay. Then another interesting point is that we searched for a healthy fluid. So we imposed, if you want, W larger than -1 always. Now, of course, this is subjective. You can do it in many different ways. So we did some simple-minded approach. We assume that the Taylor expansion around the present epoch is the same as in W0WA, but then, so it's linear in the scale factor, but then whenever it hits -1, we put it equal to -1, okay, just by a step function. In this case, we have 2 parameters. One is the value of W0 today, and the other one is the redshift at which it hits -1. It's still a 2 parameters model, but by construction, it can never go below -1. It's simply cut off by hand. Interestingly, the fit in such a model, which we call the ramp model, is not as good as W0WA, because the delta chi square, instead of -18, is only -12. Okay, but it's still much better than lambda CDM, because well, -12 is pretty large, let's say. Okay. From the point of view of the parameters, first of all, the best fit is around a very recent jump at redshift, quite small, and it's actually mostly driven by the supernova, this small number. We can interpret with this Ike criterion and which penalizes delta chi square by the number of parameters, and this gives -8, which is pretty strong, between moderate and strong evidence. Okay. So even without invoking phantomness, we still have some evidence for this. And the most interesting feature is that we can embed it in a healthy scalar field model. How do we embed it? Well, there is a standard procedure from the energy from W to reconstruct the potential. You just apply this procedure, and the potential for a scalar field that has exactly the ramp behavior looks like a plateau region and then a very steep region. Okay. This is a quintessence model with a peculiar form of the potential. Okay, one can also wonder how well do other quintessence models perform with this more standard potential. This is often called the towing dark energy, and the DESI collaboration had a paper in the first release, but you can see that in this first release, the improvement in chi-square was not very good. It was only -5 for this parameterization called towing algebraic dark energy. And this is the name that they gave. However, the ramp does considerably better than this. However, in the new DR2 release, there is also a new fit from the towing algebraic parameterization, which gives -13, while W0 WA gives -21. So now the towing solution is not bad, I would say. In the new DR2 release, we don't have the number for the ramp yet. We are working on it. Okay. Then let me stress, if I still have some time, please let me know when 5 minutes are left. I will stress the role of supernovae. Okay, so there was so let me say there was a paper by George F. Statue. I will comment later on this, and then we also had a paper on this, where we noticed that the DES dataset has essentially a quite large jump between low redshift and a high redshift supernova. You can even almost see it by eye. Okay, and now I tell you exactly what this implies. So what we tried was that we attempted a combination of Pantheon supernovae with DES supernovae. And the most naive way to do this combination is to remove the ones which are in common, because they are not completely independent data sets. So Pantheon in particular is a very sparse collection of many catalogs. DESI is much more uniform, but at high redshift, it's just one single experiment. But at low redshift, it uses also all the supernovae. Okay, so we stress the fact that this old supernova sample is crucial, actually. More than if you just use the one at high redshift, you don't get almost any interesting constraint. Okay, so this is the number of supernovae in the DES catalog, high redshift and low redshift. These are old ones. However, these old ones are also in Pantheon Plus, right? So, however, we notice that this commons data set looks different in the two catalogs, even if they are the same data points. Okay, and this was noticed by F-Statue also. In particular, if you plot the common subset, this is the common subset. In black is the DESI table, and in blue is the Pantheon table. So you can see that DESI table has an offset between low redshift, which are systematically high, and the high redshift, which are systematically low. Pantheon instead seems more centered.
We have 5 minutes left.
Okay, thanks. Pantheon instead seems more centered around 0. Okay, and this is the main feature actually. We did the following exercise. So we built 2 new data sets where we remove the common subset. So I call DES bar and Pantheon bar. Okay, we just remove the common subset. And then we combine them in two ways. So we can combine DES bar with Pantheon, or we can combine Pantheon bar with DES. There are two ways. In principle, they should naively give the same, but in practice, they do not. Okay. And actually, what happens is that this combination, DES bar plus Pantheon, gives the same evidence for W0WA as Pantheon alone. Instead, the Pantheon bar plus DES gives the same evidence as DES alone. Okay. So this means that the role of the common subset which has been removed is crucial, is fully responsible for this difference between DES and Pantheon. Okay. We can also do another exercise. You can allow for a free offset by hand in the low Z and high Z supernova in DES, and then you see that the evidence for revolving dark energy vanishes. Okay, so there was a clarification very recently by the DES collaboration about this difference in the common subset compared to the Pantheon data. And they explain that half of this offset, about half of it, is actually due to a different bias subtraction in the new catalog, in the new DES catalog. Okay, so they need to apply some corrections to the supernova distance that take into account, for example, the fact that you cannot see, there is a selection effect. You cannot measure supernovae which are too faint, and therefore this has to be corrected. However, the way they do the correction is different compared to Pantheon, and they claim to have a better bias subtraction because they have some better simulations. Okay. This becomes very technical. However, what they show is that they actually also reanalyze the DES data with the old bias subtraction. And then in this case, the evidence goes down from 3.9 to 3.3. So conversely, we can anticipate, I think, that if we apply the new bias subtraction by the DES collaboration to Pantheon, the evidence would go up conversely. So that's the situation. So let me go to my conclusions. I don't think I have time to speak about neutrinos unless maybe we can do in the discussion section. So my first statement is that interestingly, we could accommodate the H0 tension below 2 sigma level because of new DESI measurements by invoking a dark radiation fluid model, which is produced after BBN. However, very recent data from ACT rule it out, essentially. Interesting, and we are, of course, waiting for an independent confirmation also by SPT of this measurement. Instead, if we focus on cosmology, ignoring the H0 tension completely, as you know, as this has been discussed also in the previous talks, data prefers time-dependent, time-varying dark energy. However, what I wanted to stress is that this is not necessarily phantom, because still non-phantom model like quintessence model can fit better than lambda CDM, not as good as phantom model, but something in between. Okay. Also, I have shown that there is a relevant role, a very relevant role in this evidence due to the jump between low redshift and high redshift supernovae in the DES catalog. Finally, just a final remark, new data are coming out soon, as you know. So Euclid will measure again BAO. CMB, I mentioned already SPT, there will be also Simon's Observatory. And from the supernova side, more catalogs, for example, these two, which are new catalogs that should appear soon on low redshift supernovae. So maybe all this new data that will soon appear will clarify some of these points, hopefully. And I think I'll stop here.
Thank you for the nice talk. Maybe let's go to the panel discussion session, and there will be scope for people to ask questions right over there. Subinoy, are you there?
Yeah, you can hear me?
Yes. So we welcome Professor Subinoy Das from IIA Bangalore. He is going to lead our panel discussion session. Please take it over.
Thank you. So as we have not taken the questions, maybe do you have any questions for Shadab for the first talk? Then we can move ahead. Anybody has any questions? You can raise your hand. Yeah. So, can I ask you, Shadab? Yeah.
You're the chair, you decide.
Yeah. Okay. No, I was thinking to ask you. So what happens to the, because I am not from the data side, but from theory side. So what happens to the W if you go to a little bit at higher redshift? Because we know that it crosses, but when we do a model, we know how W evolves in higher redshift also. We have to match that also. Is there any hint that it keeps falling, or you can tell something about it?
Yeah, so right now it's also a function of parameter, right? Since we do not have the ability to constrain this at all redshift. I hope you can see this plot.
Yeah.
So given this parameterization, what you see is that as you go to higher redshift, W starts to saturate with large error.
Yeah.
Right. And you could do a different parameterization. For example, you could put a limit on this being non-phantom as discussed in the third talk, in which case it will approach -1 if you apply that condition. You could also do Gaussian if we do bin. So you can also see this bin measurement. The bin measurement have large error bar, and it keep going negative, and we do not know what's going to happen to higher redshift. The error bars are very large right now if you look at the bin version. So the reason this is not that large because you are using a specific parameterization. You could also do Gaussian process, and that gives you similar result to what is there with larger error bar. So more or less, if you work with any parameterization, it seems to be saturating at some value. This will depend on what the parameterization is, and it's saturating below at W less than -1. And if you put this constraint that you don't want to go phantom, then it will saturate at -1, right?
Okay. But in future, like, can we go to higher redshift more than that, or means it saturates, but can something dramatic happens in much higher redshift? Because I think DESI does not constrain that, right?
Right now, DESI data goes up to, if you include Lyman alpha, the far edge of the good data is as much as redshift 4, but the BA is at smaller redshift, the mean effective redshift. The bigger difficulty is that the effect of dark energy becomes weaker, right? So even if you have data, you're more sensitive to omega matter rather than dark energy. So it's not necessarily that having more precise data will reduce equation of state directly, but what may happen when you have measurement at these scales, this may improve your constraint on omega matter even beyond what CMB is doing right now. If that happens, then in certain parameterization, you can effectively reduce the constraint by reducing omega matter, because as you open up dynamical dark energy, omega matter become pretty uncertain. That's one of key challenges. And so indirect effect is going to be there, I think, on equation of state by improving high redshift. And in fact, DESI is planning to do a next generation of experiment called DESI 2, where it's hoping to go to higher redshift and then have a BA measurement pretty high precision at higher redshift, because that will help you look at the omega matter more precisely.
Okay. Great. Anybody has any questions or comment on Shadab's talk? Anything? Anybody, you can raise your hand, or you can type the questions also if you want. Or later we can come back. If we have any questions for Adrian's talk or Alessio's talk, anybody? So I have like Adrian, you can hear me? Yeah. So when you were showing that, the neutrino, the suppression because of the free streaming, so that is, DESI take the linear perspective. People people say that if we go to nonlinear thing, it might change things drastically. You have any comment on that? Anybody has done the DESI, the latest thing?
Well, actually, let me share the screen again. Actually, the analysis of DESI extends up to K 0.2, so you are entering to the mildly nonlinear regime.
Yeah.
So here.
Yeah.
So that is the limit of our modeling that we have up to now, because it's very complex as well. As I have shown previously, you have a lot of terms that you have to control very, very, very good. And probably you cannot go much to much smaller scales, because also if you go to even smaller scales, you start to have to deal with the variant feedback effects. So it's much more complex. So I think that at the moment is the safest way. I mean, we are pretty sure that up to here the modeling it's okay.
Oh.
And I think that you don't gain that much to go into even smaller scales.
Okay. So if you do like proper n-body and all this thing, you think it will not change that much, the result? Yeah.
The problem is that if you do proper embody, you should also implement proper hydrodynamics.
Yeah.
I know there are plenty of attempts to model this, like for example the Camels project and the Quixote project, running hydro with different hydro models. But I think this is still uncertain at the moment.
Okay. Okay. Thanks.
So maybe if I may ask a related question,
Sure.
just
Yeah,
on
go
the
ahead.
very same slide. So can you clarify what is the relative importance of the full shape analysis and compared to DESI just BAO on neutrino masses? I mean, how important is this effect, or is it mostly dominated by background only?
If I'm not mistaken, from DESI BAO you cannot measure directly the neutrino masses. What you can determine is the evolution of the background. So basically, you can break the degeneration that you have between the CMB data that is very quite prior, and you can put a constraint in this NS, which is what it leads to the constraint of neutrino masses from the BAO. But with the full shape analysis, the advantage that you have is that you have access, or you are fitting directly the power spectrum of the tracer, and you can directly measure this. So, yeah, I don't know if
Can you maybe show the previous slide with
this
the
one?
number? Yes.
Yeah.
So, for example, here I see BAO only against the full shape plus BAO, right?
No, this is BPN. Here is only.
No, in the left side of
Yes.
Yeah, the last two lines.
Yes.
If I compare. So adding full shape changes from 0082 to 0071.
Yes.
So what about DR2? Because in DR2 we only have the one from BAO.
Yes.
At the moment, but do we expect to get something better when we will have a full shape DR2? Or
yeah, I think so. I really think so. I think that the DR2 full shape analysis will be public by the end of this year. Not sure exactly the dates, but I think that is the time scale. But yes, I think that it will improve the constraints. And also this raises the issue of what I was saying, right? These constraints came by assuming lambda CDM. If you are more flexible and allow also to constrain dynamical dark energy models like this Notari, then you are constraining less the neutrino masses. And well, maybe this is hinting that either the WA can solve this issue with the neutrino masses, because currently we are approaching, I think that the limit from neutrino oscillation is 0.05. So we are getting too close to that threshold, and maybe you should start thinking that if lambda CDM is giving this, maybe we are assuming something which is wrong, right?
But that value depends on the parameterization, no, of the dark energy equation of 0.07. Means if you go to CPL, it relaxes, no?
Yes, yes. For example, is this value, right? Is 0.1. I mean, it's not that constraining because you are adding a new parameter to your model, so it's normal that you get like wider errors. But yeah. Also, one thing that worries the community is that the peak, you don't even see the peak when assume lambda CTF, like while for W not WA, it seems that the peak of the distribution is around here, right? So
It's like peak. Okay. Anybody has any questions for any of the speaker? You can raise your hand.
I have a question.
Amran, yeah.
Yeah,
For whom?
Alessio.
For whom?
Alessio.
Okay,
Yeah.
Alessio.
So in your talk, you talked about this dark energy fluid that you incorporate, the dark radiation fluid. So can you tell me that for perfect fluid, what are the implications or probes in the cosmology that will happen? Because you said the other one there, you will have shifts in the peaks of the CMB, and also there will be a cutoff in the power spectrum also. But for perfect fluid, can you a bit explain what will happen?
Well, okay, so in both cases you change the damping scale of the CMB.
Okay.
Silk damping, if you want. This a large L in the same way. Well, the reason is just that you are injecting more. You are changing age. Okay. Moreover, the free streaming case also induces a phase shift of the CMB. Okay. While the fluid does not. So they are a bit different. That's why the fit is different. There is another effect which is due to the fact that we are considering production after BBN. So because we do not want to change BBN. And the other effect is, well, we are changing delta N effective only at recombination, not at BBN. So predictions on the abundance of helium, Y helium, are standard. We are not changing those. Okay, so usually they depend on an effective, but in our case they do not depend on an effective. So that's another different aspect, and it improves the fit a bit actually, because the fit prefers the Y helium that we have in lambda CDM. We don't want to go in that direction. Actually, we would like to go in the opposite direction. So the fit prefers smaller and effective, if you want, at BBN somehow. But yeah, the main problem at this point is this ACT damping tail, which seems to completely exclude the scenario.
So Alessio, I have a little question on that thing. Because I have worked on some model like that, that for Hubble tension, people has worked with steps in dark radiation. I mean, so when ACT rules it out, you take a constant, like a sudden jump. But if you do a redshift dependent and effective, say some annihilation, then have you thought about it, whether it can do better or no? Because that actually solves Hubble tension a little better than a constant and effective.
Yeah, that's so. Do you think it would help, or
it will go in opposite direction? So
yeah,
there is a rise in ineffective smoothly, say in between BBN and CMB.
This is something that maybe it's worth thinking about. I have no clear intuition if this goes in the
we can get in touch with you. I have worked with Neil Weiner, my advisor, on that. Like, there is some particle physics model where you rise smoothly. So
it's reasonable.
It's interesting to check whether ACT does it rule out, or does it become better.
Well, in general, it seems to constrain all possible.
All possible, yeah.
But maybe it's less constrained. Sure. It's interesting, yeah.
Depends on the scale of the horizon where the N is rising. like the ineffective, the
Yes.
sound horizon side is not sound, the Hubble horizon.
Yeah,
Yeah.
you will probably have a specific redshift where it becomes
Yeah.
irrelevant.
Yeah.
So a
Yeah.
specific scale where the effect becomes relevant.
Yes.
Yeah, worth exploring, I think.
Yeah. Okay. Anybody has any more question or any comment? Anybody? You can unmute. Yeah. So, Shadab, as you know, recently we just before DESI result we did that interacting dark matter, dark energy with yeah. So so if so, how much seriously like now it like the flood of models are coming up after the DESI result, and people are doing FR and all these things, axions by the dark matter. So now, as a theorist, like we should take it serious, because as he was saying that lambda CDM means throwing model still means W greater than -1 and still okay. Means once you have to go below -1, then we have to do something dramatic. No, if we don't do phantom. So what is your comment on that? We should really think about, as the cosmologists or particle physicists, that we need that, or we should wait for something.
Yeah, I mean, so right now we are in low signal to noise regime. But if you look at the data result carefully and the caveats of parameterization, what you will notice is that the dynamics of dark energy at low redshift, which means equation of state changing, is fairly robust. But the W crossing -1 is not that robust. That will depend on how you parameterize it, what the signal to noise is. And so the effect of W crossing -1 also means that the dark energy kicks earlier. So there's also a deviation from the nano-CDM at higher redshift than just the lower redshift. And so that part is also not that robust at the moment, because the W crossing itself is not the robust. So I think what we can take very seriously is that the dark energy dynamics is shown at low redshift, and I'm expecting this to be very clear when LSST supernova sample is going to become. As Alessio pointed out, the importance of supernova, especially at low redshift, right? The number of supernova at low redshift is fairly little, and that's where the dynamics seems to be happening. And so if we have, between redshift up to redshift 0.3, below redshift 0.3, if we increase the supernova even by, the supernova numbers are really intense. And so if we increase it in hundreds, that will have a remarkable effect on dynamics of dark energy, whether this will stay or not. I would not take the W crossing -1 too seriously right now. It's sort of a very minor hint, and we'll have to wait for more data to see if it's actually.
But it has to be increasing to lower redshift.
At lower redshift, that's what I'm saying.
That is for sure.
The dynamics seems to be pretty robust, like it has to change at lower redshift. But whether it crosses -1 or not, I think that's not something very robust.
So it's kind of like a cosmological constant, but at recent time going a little bit above -1.
Yeah, so yeah, maybe some quintessence scalar field models will also be able to explain that.
Yeah,
if you don't take that W -1 crossing very seriously.
Yeah. Okay, great. Okay, then. Anything else? Otherwise, anybody has any comment or question? I think it's already people 5:30 almost. So thanks a lot. Then, yeah, it's such a nice talk, and all the way. It really kind of makes all the important point people should know, especially for us, like who doesn't deal with data that much. I got quite a bit. Okay. Yeah. Thank you. Yeah.
Thank you.
Thank you very much.
Yeah,
Thank you.
Bye.
Thank you everybody for joining. Thank you thanks to speaker for the talks, and thank you Subinoy for arranging the discussion. And hopefully sometime we will have more data and more new physics to talk about.